This presentation discusses some ideas that have evolved from my experience in PARTS, PANs, and SANs, the plain old telephone system, pretty amazing new services based on the internet and the storage area networks over the last 3 decades, starting with my career in Bell Labs in 1980. The animation shows a generalized von Neumann stored program computing model exploiting the parallelism available in today's mini-core computing chips. The new computing model defines a managed Turing machine that is programmable to implement self-configuring, self-monitoring, self-repairing, self-protecting, and self-optimizing workflows based on business priorities, latency constraints, and workload fluctuations. A signaling network overlay over distributed networks of SPC nodes allows programming end-to-end fault configuration, accounting, performance, and security management of the business workflow. Perhaps these ideas are worthwhile or perhaps not. Only time will tell. I'll spend 10 minutes presenting the ideas, and an 8-minute video shows a proof of concept implementation. The agenda is as follows. I will briefly review the hardware upheaval and the von Neumann bottleneck. Then I will present a possible solution using a parallel and network-based computing model. I say possible because it's just an emerging idea and requires validation. I will discuss then a potential new operating system implementation based on this computing model. I emphasize potential because the history of the evolution of current OSs is filled with lessons on wasted billions. Does anyone remember Multics or OS2? Unmet expectations. Who would have thought Unix, the original System 5, would vanish? Surprise winners, Windows and Linux. And stealthy survivors, of course, a Mac in a Mac. Finally, I will present a video of the proof of concept of the operating system. There are at least 3 mini-core server products that are advocating a replacement of current generation blade architecture for their cost savings based on power and space savings alone. These hundreds of cores with parallel threads supporting 64-bit architectures and high bandwidth are causing the hardware upheaval. We argue that the software innovation is inadequate to exploit the parallelism and the performance offered by these servers. This picture shows the transition of a data center from current blade architecture to many-core servers. While the new class of processors offers parallel processing and multi-thread architecture, the operating systems that have evolved over the past 4 decades are optimized to work with serial von Neumann stored program computers and do not exploit the new features fully. One example of today's use of these servers employs multiple images of Linux in the same enclosure with TCP/IP communication between them, thus wasting high bandwidth available. In a distributed environment with shared resources supporting many applications and customers, end-to-end transaction time is no longer controlled by the operating system alone, and many management systems along the path have usurped this role, resulting in high operation and management cost and complexity. The ROI calculator from a vendor of virtualization products shown here gives the breakdown of savings and costs with virtualization. The 2 key points are the saving on power and space is very high, but there is new cost associated with virtualization and its management. The upshot is that the 10x improvement provided by the hardware advances are reduced to only 2x by software and its management cost and complexity. In a distributed von Neumann computing network, Service and its management are no longer controlled by the individual node OS in a shared resource environment. Many network storage, application, and virtualization management systems intervene. The dime computing model exploits parallelism in many core architectures to separate the service and its management into parallel components. The new computing model defines a managed Turing machine that is programmable to implement parallel threads of configuring, monitoring, repairing, protecting, and optimizing the execution of a von Neumann computing program in the same core executed by different threads. The computing workflow at the node level is thus controlled by the service regulation component of the dime computing model. A signaling network overlay over distributed networks of dimes allows programming end-to-end fault configuration, accounting, performance, and security management of the business workflow based on business priorities, latency constraints, and workload fluctuations. We have implemented the dime computing model in a multi-core server, converting each core into a dime with self-management and signaling ability. We have used a service orchestrator to create the service module with its regulation and execution modules. The service orchestrator also allows the deployment and management of the service as a workflow with runtime control. The paper in this conference, Parallax, a new operating system for scalable, distributed, and parallel computing, by me and Ian Saylor, describes the full details. The demo video demonstrates three servers, each with 2 dimes, demonstrating the following features: the dime instantiation, the discovery of the dime network, workflow orchestration, scaling, dynamic reconfiguration, and fault management. The proof of concept video can be seen at www.youtube.com/user/kavaobjects. This slide shows the service deployment using 3 different components. The first component is the service component development, where the service is created by a service developer by composing the service regulation package and the service execution package. The second component is the service workflow creator, who creates a service workflow delivery by deploying the service components in the appropriate nodes. The third component is the service runtime management, which essentially allows the end-to-end service management during runtime using the FCAPS management modules. We end this presentation with 2 relevant quotes from von Neumann, who had the limitations of SPC model on his mind. We want to conclude this presentation by saying that the dime network architecture, the DNA we propose here, supports the genetic transactions of replication, repair, recombination, and reconfiguration. Thank you.